Hi there, I'm Brian Berzin, co-founder and CEO of Thea Energy. I'm excited to be back again this year to give you some updates on our recent progress. As a quick refresher, Thea Energy is a spin-out of the legendary Princeton Plasma Physics Lab at Princeton University. PPPL is one of the birthplaces of fusion research in the world, and actually was the place where the stellarator, our flavor of fusion technology, was first invented. That was about 70 years ago. Those 70 years were critical for the scientific research and development that was required for private startups to think about commercializing a technology. So over those 70 years, government-funded research, academic research pushed forward the stellarator from the theoretical basis actually through to the completion of large-scale integrated devices that ultimately showed a high triple product, high fusion conditions being achieved. And also they gave us codes and computational tools that were benchmarked against real system performance that allow us to optimize and engineer better stellarators and better power plants based on these scientific foundations than ever before. The stellarator has always had some just really important advantages for the commercialization of fusion energy, and those are related to its steady state nature and its low recirculating energy. That's really what a power plant needs to be, a device that works continually and that puts a lot of energy onto the grid rather than having a tremendous amount of energy needing to be recirculated into the device to power a pulse or a laser or a center solenoid. However, there's always a however for fusion. The precision and complexity of making that three-dimensional kind of French crawler-shaped configuration of the stellarator has always been very limiting. Most stellarators that have been built and operated across this world went significantly behind schedule and over budget. And that is unacceptable for the commercialization of a technology. And so this is a picture of W7X, the large-scale integrated stellarator in Germany. And yeah, it's a feat of science, it's a feat of engineering, but it really showed this Achilles heel for the stellarator. The superconducting magnets that are required by these traditional three-dimensional modular coil stellarators, they're massive, massive pieces of hardware that require precision on the level of a millimeter. And that precision, no matter whether it's fusion or aerospace or other types of hardware, precision and complexity in hardware are just incredibly costly and incredibly time-consuming. That device was 10 years behind schedule and went 3x over budget. If you're building a power plant and you deliver it 10 years behind schedule and 3x over budget, you're not selling many more power plants after that. The reason why we decided to found Thea Energy and spin this out of Princeton Plasma Physics Lab about 3.5 years ago was because we applied what is actually a fairly well-known type of control system called a phased array to fusion for the first time. Phased array control systems are how radar systems and cell phone towers and GPS satellites work, and allows us to use much smaller discretized hardware, and on the back end with a software stack, individually tune independent variables. So to be clear, we have not eliminated any precision or complexity. We've just transferred quite a bit of it out of hardware and onto the software stack, onto the control system. And that's where we have almost like software-like scalability. We've built the control system. We only need that control system. It's the same control system for every single magnet in the array. That allows us to actually take a bunch of hardware, some of which have defects or wear and tear or were potentially mismounted. And we talked about this a bit last year. Allows us to take all that hardware, even though things might not be perfect, and to tune them into perfection using software. That was the game changer for us. From there, over the past 2 years, and even more recently since the last webinar, we've continued to get really good at scaling the manufacturing of our core magnets. The magnets that we utilize, there are about 300 of them, and they're all the same. And they are mass-produced. They are mass-produced via manufacturing technologies that are pieces of metal that are stamped and forged in the winds of the superconducting magnets. They can be done in tension, all in one plane, around a bobbin. The Lego block of a superconducting magnet is called a pancake. We can mass-produce these pancakes and then stack them to the appropriate magnetic field spec magnet, all on the same manufacturing line. And these are manufacturing lines. You can probably see the very small video window behind me. This is a manufacturing line that really resembles an automotive plant, not needing 3D printing, additive manufacturing, extreme precision. This is something that truly scales. And we've actually now built these full-size integrated magnets. And from here, over the next couple of years, we're really focused on scaling the production. So we can make one magnet every week or two in this very small manufacturing facility behind me. We're about to take a second manufacturing facility about a mile down the road here in New Jersey, where we will scale a manufacturing line to produce one magnet a day and more. That is ultimately how we can build many power plants across this world via high throughput manufacturing that really resembles every other industry out there, not super techy, difficult to manufacture fusion. Well, we probably can't go a day without hearing about AI, so I wanted to spend a couple minutes here talking about how we utilize AI at Thea Energy and how it's being utilized across the industry. So across the industry, no matter what architecture, AI via surrogate models is utilized to look at much larger design universes of solutions. And then when we have a solution set that's viable, to take it and push it through a parametrically derived engineering workflow to build a digital twin that resembles the devices that we want to build. Quite uniquely, at Thea Energy, we also can leverage AI for our control systems, for the software stack that runs for us 324 independent variables. And that is a game changer for the stellarator. Most all stellarators to date are based around one design point and based around what humanity knows at that point in time when it was designed. That means that those devices can't take advantage of future breakthroughs, and there are continually better performance or even breakthroughs being made. One that comes to mind is turbulence modeling and suppression. The world will get better at those things 5, 10, 20 years out. And if your architecture is designed only for one operating point, it means you'll never be able to take advantage of those learnings. It will just have to go into the second generation. That's as good as the device will ever be. Because of our unique ability to have an independent control system in an array of magnets, we can actually, via a software level update, take advantage of those higher performance modes in the future. That means a power plant built today can be a better power plant in 10 and 20 years. And that's an important thing because power plants work for decades and decades on end. So you want to make sure that these devices have high uptime, high capacity factors, and low maintenance, and have high performance for their uptime. So this is very unique to us and allows us to, again, have the software level update to have higher performance even in the future. Speaking of power plants, a major milestone that Thea Energy accomplished just earlier this year in Q1 was the successful completion and certification of a milestone for the preconceptual design review of our power plant architecture. This is part of the Department of Energy's milestone-based fusion development program that we and 7 other awardees are a part of. And this milestone focuses on a power plant. The design milestone spanned the physics basis into a closing of an engineering architecture through the techno-economics, capacity factor, maintenance cycle requirements for the entire system. So this is what is the most cohesive look of a fusion power plant architecture to date across the industry, and one that really, why the milestone program was set up, enables us and our peers upon their completion of the milestone to really pursue putting fusion power plants on the grid in a structured, thoughtful way that can be further enabled by this government public-private partnership and cost share. What I want to highlight real quickly here as we go into the video is what you're about to see on the screen. These are the same subsystems that are utilized by other types of power generation systems that are online on the grid today, including combined cycle natural gas and nuclear fission. These are the same balance of plant technologies that have been built 1,000 times over around the globe and work at a very high, high capacity factor, high reliability that we want for fusion energy. We do not like first-of-a-kind technologies here, actually. We like that proven, resilient, massive manufacturing supply chain and high reliability architecture for the balance of plant that we can utilize and actually now work with commercial partners to deploy integrated systems. So this is a top-down view of our Helios power plant. Our Helios power plant is about a 400 megawatt device, and we'll dive in on the energy balance here in a second. This is a fairly traditional plot of land. It's about 40 acres. The fusion architecture that we've developed, Helios, doesn't need too many site-specific requirements. And as I pull up the second image here that expands upon the various subsystems, a lot of these subsystems are those same traditional energy generation subsystems that you see on those other types of power technologies online across the grid today. We are getting very good at the stellarator hull, using our planar coil architecture to reinvent the stellarator to create a cheaper, more manufacturable, more scalable stellarator fusion island. But from there, when you take the energy out and thermalize it, boil some water, turn a turbine, and generate electricity, those balance of plant technologies are fairly traditional and utilized by those other forms of power generation. So one subject that we spent a little bit of time actually last year talking about, but also that I highlighted at the beginning of the call, talking about the advantages and the disadvantages of the stellarator. One long-standing advantage of the stellarator was its low recirculating energy requirements. This actually can be shown on the bottom of the Sankey diagram. You can see this very small purple line with a label of ECRH. That's 1 megawatt of gyrotron heating that goes into the plasma, largely to dispel impurities from the core. That is the recirculating energy required for plasma heating in this architecture. Largely in this operational mode, the plasma is heated by alpha particles. It is ignited. And that advantage allows us to take the energy that gets converted into electricity and use it to be put on the grid to make power. There are other house loads. You can see them come off of the total generated electric and gross electric lines. Those are our house loads for pumping and cryogenic systems and other balance of plant systems. But largely, the electricity that gets generated is used to make power on the grid, not recirculated. And most other fusion architectures, unfortunately, have to recirculate a tremendous amount of that electricity created back to power another pulse. And that ultimately just directly impacts the bottom line of your power plant architecture. If you're making the same size balance of plant and fusion system, but the amount of electricity you have to recirculate is half of the electric energy created, your economics are going to be half as good. So a major advantage of the stellarator is that for its footprint, for its power generation on a thermal and electric amount, it is probably the most efficient energy and therefore efficient use of capital for a power plant architecture. A couple of other interesting things that I wanted to talk about today that are part of the design review and part of the paper that we recently released to archive relate to the practicality of our power plant architecture. One of them is actually just related to how you get the exhaust out of a plasma. Our stellarator architecture, similar to other stellarators or tokamaks, require a diverter, pretty much an exhaust manifold for the fusion plasma to function in a commercial environment. Historically, stellarators use island diverters or other diverters that have a three-dimensional component to them, which are just pretty unwieldy to build and also don't necessarily work the best when they even work compared to tokamak diverters. We have successfully utilized, and we'll have a peer-reviewed paper on this coming up, utilized an X-point diverter. X-point diverters are what have been developed really over the span of 30 to 40 years for tokamaks and what are being utilized in ITER as well as other industry-leading devices. We now can take those lessons learned, those technologies developed, and directly utilize them to implement a stellarator X-point diverter. Not only is that just a massive simplification of the engineering required for a stellarator diverter of any power plant, this also allows us to just have a higher performance system. X-point diverters are about 10 times better at pumping out gases than traditional island diverters utilized by other stellarators. So this is one fundamental requirement for the commercialization of a stellarator that we've now enabled here. Another one is actually just a maintenance scheme. I'd say, just a maintenance scheme. It's pretty fundamentally important to any fusion system architecture that there's a way to manufacture the components and then bolt it together on site, and then also have a systematic, repeatable, reliable maintenance scheme to replace parts when they're worn down. For instance, the first wall, any fusion system's first wall has a finite lifetime that will require periodic replacement. But also just over a power plant architecture's life, you're going to have parts of the system have wear and tear and need replacement. We now have a limited amount of parts in terms of the cryostat, which you can see on the screen. 12 sections of the cryostat, and vacuum systems are all the same. And from there, we can remove fairly traditionally manufactured support systems. You can see those things that look like erector sets on the left-hand side. Those are structural supports, and we make them out of pieces of stainless and other types of steels that can be welded together. No additive manufacturing, no in-depth, expensive manufacturing processes required there. And then the way that we assemble and replace and maintain other parts of the system can be done with a low unique part count and also via very systematic replacement cycles that resemble us kind of peeling back layers of an onion to replace those components over the lifetime of a power plant architecture. We're excited to share more about this power plant architecture coming up via peer review and continuing to build the team and technology required to deploy and scale fusion across the world. So thanks for the time today.